All right, so when we talk about your antiderivative, sometimes they do this in math and it drives us crazy. They come up with 6 ways of saying the same thing. So, right? So in algebra, the kids struggle with what we call it the roots, the zeros, the solutions, the x-intercepts. And the kids are like, why don't you just call it one thing? I'm like, I get you. But when we talk about this inverse process of finding the derivative, the inverse of the derivative is the integral. We can also call it the antiderivative. We learned about it as the accumulation function, and that is our original function. Hey, your trip projects were amazing. Some of you really knocked it out of the park, and I love looking at the time you took for either the coloring of the rectangles and the and that's one for sure that I'm definitely repeating every single time that I teach calculus, because the amount of times that I refer to it, your original function, distance equals rate times time, you were traveling for a specific time, and all those different rates that you were going when you were driving added up to your distance of how far you went. So that odometer reading, you all knew how far you went. But what was cool was we went ahead and graphed time and speed. So your miles per hour or your feet per second, when we translated those units, they gave us the graph that is the derivative of your original function. And then you were able to draw all those little rectangles. You were able to add up the area of all those rectangles. And the only thing that I consistently took off points for amongst everybody across the board was a lot of you didn't close the loop on kind of putting a bow on it and connecting what we were doing. So what I wanted to see was, hey, I drove 7.5 miles, and when I added up my left-hand sums, it turned out to be just under 7 miles. When I added up my right-hand sums, it was a little over 7 miles, but my midpoint sums were the most accurate because it was the closest to what I actually drove. So it was cool to see that whole process of your finding all those rectangles and taking the area of them and adding them all up, ended up giving you that output of your original function, distance equals rate times time, how far you drove. And what was cool was what we would do distance equals rate times time problems when you were in algebra, but we assumed some kind of linear situation. Well, everybody knows from the minute you get in your car to the minute you get to where you're going, your speed is not constant. It's not a linear story. It's not a constant rate of change. There's no slope. So having the ability to calculate those values under a curve is pretty darn cool. That's the whole idea of integration. So we can talk about it as our original function. We can talk about it as our position function. We can talk about it as the integral, the result of doing integration, or you could call it your antiderivative. So all of those things apply. When it came time to making these notes for our conversations on Riemann sums, now granted this picture didn't copy real well, so go ahead and grab a color pencil or do whatever you need to do to make sure that you understand. And the one thing that is so important is if you're looking at a graph, and this graph, I don't know, I'll draw it twice. Let's say I'm doing this graph here, and let's say I'm doing this graph here. If I'm doing Riemann sums, and I'm doing left-hand sums, the more triangles that I do, or triangles, the more rectangles that I do, the more accurate of a reading I'm going to have when I'm finding that area under the curve. So that kind of brings us down to when we first started talking about that summation notation. When we first started saying, okay, when we talked about whatever range you were on. Is that Anthony's?
Yeah, that's mine.
You wanna come take care of that for us? That'd be great.
No, this is popular.
How about it? And that's funny because it's off and away.
And it's my mom. Solid.
You're like, dude, mom, I'm trying to pass calculus.
Mother's right.
So when we're talking about on that interval from A to B, that distance that we find from B to A, when we subtract them, tells us that area where our interval is. Our N is going to talk about how many little rectangles I'm going to draw, and that number of rectangles represents that change in X that we have. So when we talked about this summation notation, this A was my lower bound, this B was my upper bound, and what we're talking about here was this f of x was my output of my rate function, and this change in x was going to be the width of each rectangle. So you were taking all those areas, length times width, and adding them all up between those two boundaries. So that summation notation is that bridge that we did between doing our Riemann sums and figuring out the integral. And it's interesting, just like the limit definition of a derivative is the bridge between our functions and those rates of change when we did our derivatives. Okay, so we really only have one main rule. We only have one main rule when finding the integral, and that is our power rule. And it's important that you recognize that there's no product rule and there's no quotient rule. We have those rules for derivatives, but we don't have them for integrals. So what we need to do then is look for ways that we can simplify. So if we have functions, we can use the distributive property. So we're going to look for ways to simplify, because we can deal with the negative exponent, right? But we don't have the product and quotient rule for integrals like we do for derivatives. All right, so your trig rules and your exponent rules read backwards from your derivative rules. So they're there for you to use as a reference when you are taking your final. The only thing that I really want to add, we'll talk about the fundamental theorem for calculus in a minute, but I want to also take a minute and talk about U substitution. Because if you're in a situation where you can't simplify it, then U substitution is going to be your strategy where you're going to replace your inside function with a U. And then remember, we came over and we found the derivative of that, solved for dx, and then that was what we substituted back in to help us work with U substitution. We'll do some of those later on today. Make sure you have a chance to ask your questions. So our fundamental theorem of calculus is really what it's all about. If I have a continuous function on the interval a and b, then I can go ahead and integrate that function, and then I can go ahead and calculate its value on my upper and my lower bound, subtract them, and then I can continue, then I can figure out what that area is. My only thing that I would remind you of is don't forget about the chain rule if you have those embedded functions, because you're going to have to make sure that you're careful of what it is that you're doing with those embedded functions. All right, that being said, I want you to find a partner, and I want you to tic-tac-toe. Are you finished with the quiz?
Yeah.
Is it in my inbox? Okay. So let's have Anthony come on over and sit in Jacques' seat. And you can tic-tac-toe with Simon. Did you get it at warm-up?
No. Oh, wait, yeah. On the back.
All right, so come back. Come back. On the scale of tic-tac-toes, this one was
Toe.
a toe.
Toe.
So this first one lists 3 synonyms. So the accumulation function, integral, and original functions on the back. Okay, this second box, when you FOIL first out or last, then you can go ahead and take the integral. So then this becomes x to the 1 more power, divide by, and then this becomes x to the 1 more power, divide by, x to the 1 more power, divide by, x to the 1 more power, divide by, and then you have your plus c. Your plus c is what you have when it's an indefinite integral. And then, of course, whatever you can simplify with x minus x squared plus 1/3 x cubed minus 1/4 x to the 4th plus c. And the conversation about this is it's a multiple choice test. So whether you're finding your answers in this format or that format, you need to be able to recognize both. Okay, so this one, yeah.
Shouldn't the 1 when you FOIL it be a 2?
Oh,
Minus 2x?
I know. It's a bad day for me. I'm just so heartbroken. So you can put a smart ass. Okay, let me try it again. 1 times 2 is 2. Negative 2x, inside product, outside product. Am I okay now? So then this 2 becomes a 2x, yes? And then this is a 2x. Do we like that better? Okay, phew. All right, so this one you can't do because we skipped the parts about, do you remember from trig when we did when we were using the inverse sine and cosine and tangent functions to figure out what the measure of the angle was? It was your arc sine, your arc cosine. We kind of renewed that from what we did. So when I was pinching problems, I was going too fast and somebody was talking to me, so I not only put it there once, but twice. So we're going to go with that one's not a good one. But this one's tons of fun because we want to make sure you have the difference between an indefinite integral and a definite integral. And the indefinite integral has the c, so you don't know where you stop and start, and you don't know what the constant is. Your definite integral is going to be when you find that area under the curve from this A to B inside that boundary. So you go ahead and use your power rule. Go ahead, find my mistake here. I'm sure it's there. Where you integrate, and then you want it. This is your fundamental theorem of calculus. You're going to plug 1 in, and then that is going to be subtracting your lower boundary. And when I plug 0 in, all those go to 0. So I got 1/3 as an answer. Do we agree?
Yes.
All right. So I'm a little relieved. Okay, so for this one, thanks to Billy, I know how to multiply exponents. Thank you, Billy. So we go ahead and we simplify that, and then we can integrate it. And then again, I love it when it's from 0 to something, because we can, when we do that f of b minus f of a, it works out in a lovely manner. So for this next one, this x can be divided into each of these three terms, and that gives me an x and a 1 and an x to the negative first. So when I integrate that, we can't follow the power rule, because if I take the power and add 1 to it and then divide, I'm dividing by 0, and that's a no-no. And so that's what takes me to that natural log of x. And then it's from 1 to e. So when I plug 1 or e in here minus 1 plugged into there, I get e squared over 2 plus e minus 1/2. Are we okay on that one? Yeah. And then this whole row is a dumpster fire, because this is one you don't know how to do, because it's got this function up in here, and you have to go on and do the chain rule, and we didn't learn that, we stopped early. And then this is a repeat, and then this is a repeat of one we can't do. So, as far as I'm concerned, you're all winners. Yay! So first of all, your final review materials. Here is Kaylee, you wanted last class's video. It'll be here. Literally lunchtime. So that's there. Here are all the PDFs of all the worksheets that we've done. Not the snake and the foxtrot, but the limit tic-tac-toe, the derivative tic-tac-toe, this applications, this derivative worksheet, that was what you did in Stinger today. And I'll add keys to these. So a couple people have asked for keys, so I will add them up, including with all the ones that are like, no, forget this, we didn't do that. Sound okay? All right. All right. So when we want to find the area under the curve between 10 and 1 of f of x using the left-hand approximation, here's the number one thing you need to look at for this. I do not have even intervals. Did you get this? I don't have even intervals. So what you have to do is you have to look at each interval separately and use the left-hand sum. Okay. So when I look at this, and again, you're talking about that change in that x value. So I have 3 minus 1 is a change of 2, and because it says the left-hand approximation, that's going to be multiplied by 17. My next interval I'm going to look at is 4 minus 3 is 1, and I'm going to be using my left-hand sum times 13 plus 8 minus 4, left-hand sum, 10 minus 8, and my left-hand sum. So I've got 2 times 17 is 34, plus 13, plus 32, plus 8. So it's at 40, 53, 87. So the kicker here is you want to make sure you know that these are uneven intervals. So you can't do any shortcuts. So a lot of you painstakingly filled out every single part of your trip project by doing the 15 seconds times 15 seconds times 15 seconds times. And then a couple of you figured out, oh, I can just add up all of those speeds and then multiply them by 15 because they were even intervals. When you do not have even intervals, you have to figure out the change in your x's for each one. Sound okay? All right. If it had been right hand, we would have used 13, 8, 4, and 1. If it had been midpoint, we couldn't have done it because we don't know any of the midpoints. So you can only do midpoints with even intervals. Okay? All right. So this came directly from a homework that you did because what we wanted you to recognize is that limit notation is what led to our conversation of the integrals. So I'm taking the sum of all of the values of this function and I'm going to be multiplying by that change of x from -2 to 2. And this is why we went back and reviewed that function family graph. You know that 1 over x is a graph that looks like this. So if I'm talking about my interval from 1 to -2, or from -2 to 2, I'm talking about drawing the graph with that interval. So we have this area under the curve and this area under the curve. Okay, so we have it in summation notation, so we can instead write it as an integral, our lower bound and our upper bound of our function. And when the change of x becomes so very small, that's what we refer to as d of x. Our square root function looks like this, and I care about it from 0 to, and if I want to call this 9. Again, the limit as my change in x approaches 0 of the sum from -pi to pi of the sine of x times the change in x. My sine function from -pi to pi looks like that. +2. If I want to find the integral from 3 to 8 of my absolute value function, change of x is teeny tiny. X minus 4 means that this absolute value is going to move to the right because it's inside. From +3 to 4, 5, 6, 7, 8. How are you feeling about page 1? No landmines. All right. This next one, find the area under the curve y is equal to x cubed on the interval with 3 subintervals using right-hand endpoints. Okay, let's talk about what that means. If this is my a and this is my b, b minus a over n is going to give me 6 minus 0 with 3 subintervals, right? You okay with that? So when I go to draw my input-output table on the interval from 0 to 6, each sub-interval is worth 2, right? So 0 to 2, 2 to 4, and 4 to 6. Here's my first interval, my second interval, my third interval. Now, this is a case where I could use the midpoint if it's left hand or right hand or midpoint. So the easiest way, it's an easy function for you to do. So 0, 1, 8, 27, 64, 125, 216. If it's not something you can do in your head, just go ahead and go to the calculator and use that. If I want right-hand endpoints, that means I'm using this guy, this guy, this guy, this guy, this guy, this guy, not that guy. Does that make sense to you? But I'm not, because it's just on these subintervals, so I lied. I'm not using these middle guys. 3 equal subintervals, here they are. So my change in x is equal to 2. So remember I said if I have an even number, if it's an even equal subintervals, instead of doing 2 times 8 plus 2 times 64 plus 2 times 216, you can factor that 2 out and just do 2 times 288, 576.
Miss Glazier?
Yeah.
When we're showing our work on a test and it asks for like a right or a left hand endpoint, do we have to do the middle numbers on our chart?
No. No. I wanted to go ahead and show you guys that this is an example where you could do the midpoints, but if you don't include this, that's fine.
Okay, thank you.
All right, x, f of x, 1 to 9, my change in x is equal to 9 minus 1 divided by 4. So again, 2. So when I'm talking about 1, and if you wanted to, Catherine, you can just do 3, 5, 7, 9, right? Just to show you what it looks like on the calculator, even if you can do this stuff in your head. Go ahead, do x squared plus 2. Go to your table of values, second table. Go get the value when x is equal to 1, when x is equal to 3, when x is equal to 5, when x is equal to 7, and x is equal to 9. Oh, I do need midpoints for this one. Darn it! Wow! You guys should have said something. Here I was thinking I was being efficient showing you. That's okay to 3, 4, 5, 6, 7, 8, 9. So 3, 6, 11, 18, 27, 38, 51, 66, 83. My 4 sub-intervals, 1, 2, 3, 4. So I care about this number, this number, this number, this number. Can I do it the fast way? Two times 128, 256. There you go. All right, so if we're given just a generic function, we have to use this graph. The graph of function f is given. List the integrals from smallest to largest. So the area under the curve from 0 to 9, right? And then we have from 6 to 9, 0 to 5, 0 to 6, and then f of f prime of 5. Ready? So if we go ahead and we count our integrals. One, two, three, 4, 5, 6. We can go ahead and estimate, right? What do you estimate 9 as? So we can call that one, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Count that as 12. Count that as 13. So I estimate around 14 here and -2, so we're going to say this one's about 12. You buy that? All right. So from 6 to 9, looks like -2, right? 0 to 5, here's 5. 1, 2, 3, 4, 5. So I know 0 to 6 is going to be a little bit bigger. I think 0 to 6 is the biggest, right? So D is my largest, then followed by C, because this doesn't have any negatives and neither does this one. When we talk about my smallest, it's going to be B, and then A, and then what do you want to do with this? F prime of 5. If this is the graph of the function, when I look at the derivative at 5, negative, right? I'm going to put that here. All right. Check Schoology for keys.